Hello, my name is Daniel Schöler. I'm a German civil engineer and software developer, and I'm with Deep Foundation Design LLC. And in this video, I'm going to talk about the Francis Scott Key Bridge collapse in Baltimore that happened on the 26th of March 2024. And I actually am going to go into a lot of details, into a lot of structural analysis. Spoiler, it could have been prevented. And I'm going to also show you exactly how and offer a couple of solutions. So before we start, this video is dedicated to the families of the victims and their friends: Alejandro Hernandez Fuentes, Dorlean Ronial Castillo Cabrera, Miguel Luna, Mainor Yacir Suazo Sandoval. And as far as I know, there are still 2 people missing, which are also presumed dead. So I offer my deepest condolences to the families and friends of the victims. Another thing that I briefly want to mention before we start into the structural analysis and really talking about how we could have effectively prevented the bridge from collapsing is to pay my respects and my gratitude to the people that were really alert at 1:30 in the morning and closing this bridge. Great job. It's awesome to see that at night when everybody is sleeping, there are still people that are alert and really try to make sure that they show up at their absolute best, and this is absolutely amazing. So thank you to these people as well. So let's jump right into it. Let's talk about the setting of the accident. So I'm not going to roll out the entire story again. You already have seen it has been covered all over the news. So let's talk about the structural analysis. This is a picture showing the Francis Scott Key Bridge from the view of the port outwards of the harbor. And basically the way that we're going to approach this problem is we're going to take this Bravo section of the bridge, the entire trussing system, and we're going to model just one of these bearings with a horizontal force, and we're going to determine the horizontal force by looking at the parameters of the ship and trying to figure out a force that we're going to apply in order to figure out what sort of deformations that would have caused to this bearing and what sort of implications these deformations would have in the context of this bridge building. Bridges are designed to do one thing very well, and this might sound like a little bit of third grade, but I think it doesn't hurt to go over the basics. So bridges are basically designed to only withstand significant amounts of vertical loading. And they are very sensitive towards horizontal loading, and we will definitely see by the deformations that we calculate how sensitive they actually are and how important it is to really protect bridges against lateral loading, horizontal loading. Another thing, and this might be also a little bit of third grade, is that bridges are usually not designed to withstand one of the bearings getting punched out. So any bearing collapse will always result in the bridge collapsing. The main bearing and the main point of interest that we are going to talk about is, of course, this bearing that we call bearing C, where the Dali actually collided into the bridge and collided with the bridge. And to start off, we want to calculate the force. So in order to determine the force, what we want to do is we want to think about the ship approaching and ramming the bearing of the bridge as sort of an impulse. An impulse is nothing more than the mass of an object multiplied by its velocity, and the force that is generated by the impulse can be determined by just dividing the impulse by the amount of time that it took for this impulse to occur. And we're going to make some estimations here. We're going to estimate that the ship was actually not fully loaded. We're just going to say, okay, the ship has roughly 100,000 metric tons of weight, which is roughly 220 million pounds. We know that the velocity of the ship was roughly 8 knots at the time of the collision. And we're also going to assume that the impulse had a duration of roughly 5 seconds. I think these are conservative estimations. I think these are conservative assumptions. The video clips that I've seen so far really seem to underline these assumptions. So with this, we at least can get the ballpark of the order of magnitude of force that we are going to deal with. And you're going to see in the continuation of the structural analysis that with this sort of estimation, we're definitely going to end up in the right ballpark, and you're definitely going to be able to understand the significance and the absurdity of these amounts of horizontal loads and why it's so crucial to protect bridges against these sorts of loading. So if we plug all of these values into our formula, then we're going to get to 82,000 kilonewtons of lateral loading. And in imperial units, this is roughly 18,500 kip. And if our assumptions are correct, then the impulse that the Dali had while it was colliding with the Francis Scott Key Bridge had a force that is equivalent to the gravitational force of basically the weight force of 44 fully fueled and loaded Boeing 747 aircraft. So now let's talk about the system deformations. So the system deformations for us are really important to figure out what's actually going on, how this collapsed. So when I first saw this story and when I first saw the collapse of the bridge and I saw the next morning the images that were all over in the news, I realized that the concrete structure, the part of the foundation that actually is the bearing for the trussing, is completely gone. So you cannot see it here. There's nothing left of it. And my assumption was that the piling foundation, that was the foundation for this triangulate concrete structure, actually completely failed. Here you have like a schematics of it. Here you see like a little illustration that I made. So if we look at the video clip, we see, and this is something that we have to keep in mind, is any sort of deflection, any sort of movement in lateral direction that we can see here. This is a very big ship, and also the bridge itself is very big. So any sort of deflection in lateral direction that we can see in the video clip is probably upwards of 1 yard. And this will definitely derail these bearings here in the top where the trussing is connected with the concrete triangulate bearing structure. And so in the moment now when the bridge actually hits this, basically the piles underneath, and this is my best guess, is that the piles underneath the triangulate structure here, they basically snap. And what then happens is that this complete triangular structure doesn't have any support anymore, and then it's a kinematic system, so basically the entire thing is then in free fall. And my assumption is that we can actually, when we send some divers to investigate, we will actually see this triangulate structure still laying on the seabed. And this is something I can say for sure. If a ship of this magnitude hits a bridge like this, then it will definitely punch out this bearing like this, like the way I showed, and it will definitely collapse the bridge. So it's absolutely important to keep any sort of vessel away from the bearings of any bridge, and we will show in this structural analysis some protective measures that you can take to actually make sure that accidents like these don't happen again. So in order to do the structural analysis, we have to build our model first. In this scenario, I have basically taken the information that were out on the internet. For example, an NBC news article quoted that the depth underneath the bridge was roughly 50 feet. And so I have used that. So basically I have a layer of water of 50 feet. And then underneath it, I assume that there's like 6.5 feet of mud, because I think it's probably not something that they have been clearing out. So 6.5 feet of additional mud. And then underneath that, I will just assume that there is homogeneous bedrock. And if we talk about the lateral deformations that we are going to calculate, the stiffness modulus is the most important thing that we have to get right. But I can also spoiler you that with a horizontal load like this, it really doesn't matter if the stiffness modulus is 2,700 or 2,900 or 2,400 KSF. The results would have been exactly the same. The way that we are going to go about this structural analysis problem is, one fundamental problem for us right now is that there is very little public records, there is very little technical drawings, there is very little information on the piling foundation that sits underneath the bridge's bearings. So we have to make some assumptions, and we have to figure out valid comparisons that can give us a rough estimate, a rough idea on how the deformations, in which order of ballpark, in which order of magnitude they are going to be, so that we then can estimate whether or not our structure would be able to handle such deformations. And the way that we are going to do this is by introducing dolphins. Dolphins are concrete support structures that are designed to protect bridges, and they're basically giant foundation piles with giant diameters that are steel reinforced that will take a hit by any sort of vessel and probably collapse in the process. But the idea is that it will at least slow down and at least reduce the force of impact that will then happen on the main bridge structure. So we are going to consider 6 foot, 8 foot, 10 foot, 12 foot, 14 foot, 16 foot and 30 foot diameter dolphins. The last one is obviously not something that is possible with the machinery that exists today, at least not to my knowledge. Another assumption that we are going to make is that the dolphin will have a length of 75 feet. What's really interesting for us only is the horizontal forces. Here you can see in kip, we have the 18,500 kip horizontal loading that we estimated as the force of the impulse generated by the Dali colliding with our bridge bearings, and this is going to be the load that we're going to be using. And these loads are going to be the loads that we're going to use in order to calculate the deformations of our different dolphins in order to get an idea of what sort of deformations we are going to talk about. So let's jump into the design of the dolphins. This is basically how we would design a dolphin that is 6 foot in diameters. We have a circular piling structure, and we have a steel reinforcement cage, also circular. And here you can see it from the side. You can see that there's all sorts of stiffness rings, and there is a spiral reinforcements. So for the reinforcement, we have pairs of rebar rods, and it's 20 of them, so 40 rebar rods in total, and the diameter of each of these is 1 3/8 of an inch in diameter. What you can see here, that is the resistance curve of this. So whenever I design any sort of pile or any sort of dolphin, I would also always try to print out the resistance, the pile capacity basically. So the way that I usually go about proving that our internal forces are within the limits of this capacity curve is that I usually go ahead and I plot the pair of Mn that is relevant. So we have the Vd max for the vertical loading, and we have the M max that we have from our structural analysis. And then if this point, I usually design this as to be a triangle. If this is underneath the curve, then we know that we are absolutely fine. I have a very good example for this on my website. Here you see a set of, I think it's 200 piles. And what you see is here in green on the right hand side is the pile capacity curve. And you see like all of these pairs of vertical forces and bending moments for each of these piles that are plotted in here. You see all of these piles at different lengths, different deflection curves and different bending moment curves, and so on and so forth. So this is basically how it looks, and this is basically how we're going to approach the structural analysis. So now let's look at the results of the structural analysis. We're going to look at the horizontal deflections first. And what you're going to see is that here is 75 feet. This is basically where our dolphin ends. And you're going to see the figure of how this is going to deform. And on the x-axis, you see the deflection W in inches. So you see here that we are talking about roughly 600 inches of lateral deflection. So this is obviously an absurd number. So 600 inches are 50 feet. And so obviously the pile is, if it's only 75 feet long, it's not going to laterally deform 50 feet. So we already know by looking at the deflection that this is basically nonsense. So this is the moment curve. It's also not really relevant, but this one here is a little bit more relevant. And this is the pressure that the pile is going to have on the surrounding soil. And the reason why this is important is because all of these piles, any piling system, any dolphin is going to sit in the seabed. And what's really important is when we now start horizontally loading that, at some point the pressures here between the seabed, between the bedrock of the ocean floor and the pile is going to exceed the limits of the capabilities of the soil for bearing. And what this then means is that we really don't have any idea what is happening. Usually that means that the entire system is going to collapse. And for sure, what we can say is if that happens, then the mathematical model behind our calculation is not going to make any sense. You remember how on the website it looked more like this? So here we have such a tremendous load that is generated by the DALI colliding with our dolphin that we basically have so much bending. You can see that here, how initially there is no bending at all, and then this bending moment linearly increases and reaches its maximum all the way up here where the bedrock starts. And this is not good. So what this basically means is we are still 1.5 orders of magnitude away from anything that would remotely make any sense to try to bear for a dolphin like this. So I hope that made sense, that we go over the results a little bit more in depth for the first pylon, because now we're going to just look at the other results and we're going to know a lot more. So this is now 8 feet dolphin, and these are the results for the 8 feet dolphin. And as you can see, the advantage that we now have, that we have talked about in depth a little bit about the results of the 6 feet dolphin, we can now easily go here and see, okay, this is 75 feet, this is our lateral deflection. We can see that at the top it's the highest. We're roughly talking about 300 inches of deflection, which is roughly 25 feet. So still with an 8 feet diameter dolphin, we will get a result that is basically nonsense. We see again here that the pressure between the pile and the soil is exceeding the soil's limits. And we can also see again here that we are also like still at least 1 order of magnitude away from anything that would remotely make sense from an internal capabilities point of view. And long story short, the same thing is going to happen for the 10 feet dolphin and for the 12 feet dolphin and for the 14 feet dolphin. And now you can already see, when you look at the 14 feet dolphin, this is now a tremendous diameter. We're talking about 14 feet in diameter with only 75 feet of length. So now this becomes a super massive concrete dolphin. And even with such a dolphin, when we look at the results, we are nowhere near anything still that makes any sense from an internal forces point of view. This is the biggest thing that I think is possible to construct at this. So right now, from my knowledge, the 16 feet dolphin would be somewhere in the ballpark of what would be the maximum that is currently possible with the machinery that's out there. I think you would need Liebherr at least LB55, which is capable of delivering 550 kilonewton meters of torque. And this is a giant machine. It's 190 metric tons. And this is quite a colossal, and this is basically the maximum that you're going to get. No, of course, this is going to be an absurdly solid dolphin, but still, when we look at the results of our structural analysis, we are still nowhere near anything that makes sense from an internal forces point of view. So still, we are nowhere near anything that could bear the sort of impact that the DALI had when it was colliding with the Francis Scott Key Bridge. So now let's look at a fun example of a 30-foot dolphin, which is not possible, at least not to my knowledge. And just because we're curious, we want to see how this one would perform. And we can see we're slowly getting closer to the internal forces, but we are still with a 30-foot dolphin that is almost twice the size of what we are capable of constructing in the present era. And with this, you introduce a whole set of problems. For example, like what are we going to do with our 64,000 pounds of weight of the rebar cage? How are we going to get this into the concrete? And also, how are we going to get all of the concrete? These are, on a technical level, just to produce one of these it is absolutely absurd. It's not possible. But still, with a fictional dolphin that is twice the size of what we can build today, we are still 50% underneath the limit of what we needed in order to compensate for an impulse generated by the DALI on the Francis Scott Key Bridge. And then also another problem would be that we still exceed the limit of the soil surrounding the pile. So this is something that we have to keep in mind too. So why did we do this? Why did we take a look at all of these different dolphins? Well, we took a look at this because when a 30-foot diameter dolphin, completely reinforced, is not able, and not even closely able, to bear the loading in lateral direction that would be generated by the dolly slamming, colliding with this dolphin, then how is the Francis Scott Key Bridge going to resist this load? If this dolphin isn't even able to resist an impact from this ship, then this Francis Scott Key Bridge for sure is not able to handle it. And this should not come to us as a big surprise. So now let's look at real protective measures that we can do. What if we, instead of taking one dolphin, use multiple dolphins? And here I just drawn a schematics, the yellow area here, that's basically how I assume the shipping lane to be. And then here you can see the bearings of the Francis Scott Key Bridge. And my idea was, what if we just use a couple of them, maybe 5, maybe 6 of these concrete dolphins in order to protect the bridge. So basically the ship starts taking out the first, and now we know what is going to happen to the first one. It's going to get taken out and it's going to absorb a lot of energy. But what if we assume, and this is a good assumption, that after it hits the first one, it hits the second one, but with less force, because the first collapsing dolphin already took away some of the energy of the ship and slowed it down a little bit. And what if this fails as well? And then the third one has even less impulse that it has to handle, and the fourth one has even less impulse that it has to handle. So the way that we're going to approach this idea is we start with our initial loading of 18,500 kip, and we're going to assume that when this dolphin fails, it will slow down the vessel significantly, and it will probably also redirect it a little bit. And the way that I'm going to imagine this is by dividing the initial load by half. So from each pylon to the next, I'm going to always divide the load by 2. So 18,500 becomes 9,250, and so on and so forth. And then we can look at the results of the deformations of the system. And you can already see why I wanted to go over the first dolphin, the 6-feet dolphin, in a little bit more depth and show you a little bit like how these graphs are to be interpreted, because once there are multiple graphs involved, we really want to understand the basics behind it. So this is now our first dolphin, obviously, this is our second, this is our third, this is our fourth, and this is our fifth. We divide the forces by 2, and what we're going to see is we're dramatically reducing the deformation of the last dolphin. We're also seeing here the same trend. We have here the maximum, the first one, the second one, the third one, the fourth one, and the fifth one. And when we now look at our model, so the capabilities of the soil to bear these sort of pylons, we're definitely seeing that the first 4 piles are definitely being taken out, but we can almost safely assume that the 5th pile fits still somewhat into the capabilities of the soil. So we can say probably for the 5th pile now that our model is going to hold up. And when we look at the internal forces, we are also seeing, well, congratulations, like the last pile is basically within the capabilities for the internal forces of this dolphin. So what we can now see is that if we build a sequence of these dolphins, what is going to happen is still most of the dolphins are getting taken out, but the last dolphin eventually will probably stop the ship or redirect it in a significant fashion away from the bearing of the bridge. And this is huge. This is a huge finding that we can, by using multiple dolphins in a sequence, then protect effectively our bearings of any sort of bridge against oncoming traffic. And I was a little bit more curious, so I took a look at a couple of different configurations. So I was like, okay, what if 16 feet is maybe a little bit ambitious in terms of the effort that you're going to have to put in to construct these. What if we say we want to have 12 feet? 12 feet are a little smaller, so they're a little bit more easier to produce. So let's look at 6 12-feet dolphins. So here we have the 6 12-feet dolphins. Here we have the loading. The last one is only going to experience 578 kip in horizontal direction. And here we see the results. And this is the exact same as we have seen before, same model. Here we can see model holds up probably for the last two dolphins. And we see that our last dolphin is definitely in the area of where the internal forces that are generated by the now very slow Dali hitting the last dolphin is going to be able to resist this load that is generated, this force generated by the now very slowed down Dali hitting our last dolphin. And also in this scenario, we would have successfully protected the bridge from an impact. Now let's look at 8-feet dolphins. So 8-feet dolphins would be in the area of where I would say this is a normal irregular sized dolphin. So here we have the table with our 8-feet dolphins. Here we see the loading. We go with the last one all the way down to 144 kips. So here's the results. And we can see that now, at least for the last 4 dolphins, we are definitely going to have a model where we can safely assume that our calculations of our internal forces, of our deflections are correct. And we can also see that with our last dolphin, we are also going to be within the limits of our internal forces, of the capabilities of the 8-feet dolphin. So we can also say that in this scenario also, like, most of them get taken out, but the last one, the last 8-foot dolphin is definitely going to stand and resist the very, very small impact that the ship will have on this dolphin. So results, what can we say? We have studied individual dolphins and how they're going to deform when the Dali would collide with each of those. And we can safely assume that even with a 30-foot dolphin, which is a lot stronger and can bear a lot more internal forces than the foundation of the Francis Scott Key Bridge, we would basically not be able to bear such an impact. But what we can safely say is once we use a configuration like these, where we have a couple of dolphins in sequence, then the structural analysis shows that if our assumption that each of these dolphins is going to slow down the vessel, which I think is safe to assume, if that is true, then a sequence of 5 16-foot dolphins, 6 12-foot dolphins, or 8 8-foot dolphins would safely protect the bearings of the Francis Scott Key Bridge against oncoming traffic or against collisions with oncoming traffic. Why did the bridge collapse? Well, so these red circles, these red circled areas, these are the weakest links of this lateral structure. So at these points where the truss is connected to the triangulate support structure, the capabilities for transferring lateral loading is minimal. And you can sort of think of it as a train. So think about it, you have a driving train and then you start moving the tracks. What's going to happen is the train is going to derail. And this is sort of the thing that happened here. So the ship, when it hits the triangular bearing structure here, the support structure, it basically deformed it in lateral direction, the entire thing. And with this, snapping the piles underneath it. So somewhere here in a depth of 20 to 25 feet, I assume the piles then snapped, thus tipping over the entire triangulate structure. And then basically you derail these points here, and then the entire bridge has no support anymore, and then the entire thing is in free fall. This is how this bridge collapsed. Now, why would you build bridges in harbors is a very valid question, and it's not something uncommon, but it's, in my experience, very uncommon to see this sort of bridge spanning a harbor of the size of the caliber of the Baltimore harbor. When we take a look at the Hamburg harbor, which is one of the biggest harbors in Europe, They also have a bridge spanning the entrance of the harbor, but this is a cable bridge and it has a lot bigger span. And also the bearings of the pylons, they are on land, they are on shore. So even if any ship was lose power, it's very improbable that it would actually strike at these points. It's more probable that it would actually beach somewhere near these. What I want to show here is that if you build a bridge, I think it's important to give the navigational, the maritime traffic as much clearance as you possibly can, and to make sure that, if possible, the pylons, the support structures of your bridge are not going to be exposed to the shipping traffic. This is another example, everybody knows it, the Golden Gate Bridge in San Francisco, a beautiful engineering marvel of our time. And this is the way that you would want to build a bridge. It's you have a big cable bridge that has a very, very large span to make sure that you really give all the ships as much clearance as you possibly can. That's important. And as you see here in the image, you see here that there is some sort of collision barrier, but if I were the people of San Francisco and I see that in Baltimore a bridge collapsed, I would go over this design once more and I would really make sure that I look at the math once more, because the worst thing that can happen is that one of these sized cargo ships is going to lose power and then slamming in the support. This will also almost certainly collapse this bridge, and so I would really make sure to go over this one once more and make sure to take a look in depth and think about if this is going to hold up with the sorts of cargo ships that we have nowadays. Protecting bearings with boulders. That is another one that I've seen, and here's an example. This is in Tampa Bay, and I must say I'm not really convinced of this sort of solution. And the reason for this is that if you look at this illustration here, so the reason why I don't like this solution and why I'm a little bit skeptical about it is, no matter if you extend it outward further, if some sort of big vessel would approach and it would start to beach here, what's going to happen is these rocks in and out itself, they are not elastic. They are very ductile materials, so they're not going to be able to deform. And these rocks, they might be able to compact, but the question is where and what against, because for compaction you always need a solid surface. You always need to have some sort of area that you're going to compact against, and this would be the bearing of the bridge, and this is what we really want to avoid. So once this vessel would beach here, it would compact all of these rocks against this foundation of the bearing of the bridge, and then it would almost certainly snap it as well. So when I see these images, I'm a little bit skeptical of whether this is really a solution that is going to be working. So could the collapse of the Francis State Key Bridge have been prevented? The answer is yes. It could have been prevented. Dolphins, we have shown a couple of configurations in which we would have prevented this incident from happening. So now that we have talked about all the structural analysis and about whether or not it could have been prevented, and that we have gone into a lot of depth in this video, there's two more things that I want to address, two or three more, and the rest you can read in the book that is going to be on the website. So I'm going to put this on the website, and I'm also going to share the link for the PDF so that you can download it and that you can read it. And two more remarks. One is, well, what about a tunnel? So there is many examples of tunnels out there. There's even a tunnel that is connecting France with England that is roughly 30 miles long. So there is a lot of examples of tunnels and how they have been proven invaluable in the past. The advantage that a tunnel has, we're talking here, I think this is roughly 1 mile maybe, or even like 1.5 miles or something, is it's not a lot of distance, and what the advantage is, it will definitely clear the entire area for maritime traffic. So you won't interfere with the maritime traffic. So this is something for you to decide, for you to discuss. And before the last point, which is going to be the recommendations, what I want to really point out is, what if that happened under different circumstances? What if this happened when during the day, maybe rush hour, maybe there's a traffic jam on the bridge with hundreds of people on the bridge, and bad visibility, foggy conditions, bad weather, whatever it is, that could have potentially been a lot worse outcome. And so this is something that I think is up for you to think about. I don't want to comment that any further. So yeah, let's jump to the recommendations. One thing that is important to me, maybe I'm a little German and maybe I'm a little naive in this regard, is that I at least want to point it out that since the bridge collapse could have been prevented by utilizing protective measures such as concrete dolphins, I earnestly would hope that the community of Baltimore would step up, come together and provide adequate monetary compensation for the families of the victims to compensate them for their loss. I really think that is fair. And yeah, this is the end of the video. Sorry, it was a long one. And if you have any sort of questions, then you can write them into the comment section below. I will address them shortly. I'm actually on the way to vacation with my girlfriend, so it might be a couple of days before I will be able to respond to the questions. You can also send me an email. The chances that I'm going to be able to respond to the email are bigger. The email address is info@deep-foundation-design.com. If you like these findings of the structural analysis and if you like this video, then please make sure that you share it so that more people can watch it, and especially the people that are in charge in Baltimore see it. And with this being said, thank you for your attention and your time. I take that very preciously, and I hope that you have a great Easter break. Goodbye.